Welcome. Today we will build a complete understanding of the conformer, the neural network architecture that powers modern speech recognition. We will cover 6 ideas in sequence. Why speech is hard, the Mel Spectrogram Input, the subsampling front end, the conformer block and its macaron sandwich structure, 2 decoding strategies, and the most efficient variants. Speech is hard to process because the signal is non-stationary. The frequencies and energy patterns shift every few milliseconds as we speak. A transformer is powerful at capturing long-range context. It can relate any 2 frames across a full utterance, but it is relatively weak at extracting fine local acoustic patterns. ACNN is excellent at picking up transient local sounds, pitch bursts, consonant transitions, short acoustic events, but it cannot model long-range linguistic dependencies. The conformer, proposed by Google in 2020, solves this by combining both. Self-attention handles global context. Depth-wise convolution handles local acoustic detail. Together they achieve the best of both worlds. Before the network sees anything, audio must become a structured image. We sample at 16 kHz. We slice it into overlapping 25 millisecond frames using the short-time Fourier transform. We apply a Mel filterbank to match human pitch perception. Then we compress energy logarithmically. The result is a 2-dimensional image. Time flows left to right. Frequency increases bottom to top. Bright colors mean loud energy. Dark means silence. This 80-dimensional Log-Mel spectrogram is what the conformer processes. Self-attention has a critical weakness. Its computational cost grows quadratically with sequence length. A 10-second audio clip produces 1,000 frames at a 10-millisecond stride. That is 1 million pairwise comparisons. Far too expensive. The solution is a subsampling front end. 2 successive 2-dimensional convolutional layers, each with a stride of 2. Compress the time dimension by a factor of 4. 10 millisecond frames become 40 millisecond frames. This dramatically cuts the cost of subsequent attention layers. After subsampling, a linear projection aligns the channel depth with the model's hidden dimension. Relative positional encodings are then injected to give the attention module a sense of frame order. At the heart of the conformer is the conformer block. It is structured like a macaron sandwich. 4 modules are stacked in a precise order. A half-step feed forward, then self-attention, then convolution, then a second half-step feed forward. Layer normalization follows. Notice that there are 2 feed-forward modules, not 1. Each carries only half the standard residual weight. This symmetric arrangement, borrowed from macaron-net, produces smoother gradient flow during training and consistently outperforms a single full weight. Feed forward. Let us look inside one feed-forward module. First, layer normalization stabilizes the input. A linear layer expands the dimension by 4. The swish activation adds a smooth non-linearity. Dropout regularizes the signal. A final linear layer projects back to the model dimension. The output of the feed-forward module is scaled by 1/2 before being added back to the residual stream. This is the half-step design. 2 such halves bookend the attention and convolution modules. Inside the attention module, each frame generates 3 vectors: a query, a key, and a value. The query from each frame is compared to all keys using a scaled dot product. The softmax turns those scores into attention weights, which blend the values to produce the output. Standard transformers use absolute positional encodings. They assign a fixed number to each frame position. This fails on audio lengths not seen during training. The conformer instead uses relative positional encodings. Each frame knows only its distance to other frames. This generalizes perfectly to variable length audio. Multiple attention heads run in parallel. Each head learns different relationships. Some heads attend to nearby frames to track phoneme boundaries. Others connect distant frames to model sentence-level prosody. Their outputs are concatenated and projected. The convolution module is a precise sequence of 6 operations. Let us build it one step at a time. Step 2 is the gated linear unit, or glue. It splits the expanded channel tensor into 2 equal halves. 1/2 passes through unchanged. The other half is passed through a sigmoid to act as a gate. The gate suppresses irrelevant or noisy features dynamically. The depth-wise one-dimensional convolution is the analytical core. Unlike a standard convolution, it applies one separate filter per channel. No channels are mixed. This drastically reduces parameters while still aggregating local temporal context over a large kernel of 31 frames. After batch normalization, the swish activation is applied. Unlike ReLU, swish is smooth and non-monotonic. It retains small negative values and produces superior gradient flow in deep conformer stacks, leading to faster convergence. The residual connections are what hold the conformer block together. First, the half-step feed-forward adds to input X. Then self-attention adds to that. Then the convolution module adds its output. Finally, the second half-step feed-forward adds, and layer normalization is applied. At every step, the previous signal is preserved. This lets gradients flow back through many layers without vanishing. The conformer encoder produces a rich sequence of acoustic representations. These representations must be decoded into text. There are two main strategies. The first option is connectionist temporal classification, or CTC. A simple linear layer sits directly on top of the encoder. It predicts token probabilities independently at each time step, including a blank token. CTC is non-auto-regressive. All frames are decoded in parallel. This makes it extremely fast. The downside is it usually needs an external language model to achieve competitive accuracy. The second option is the transducer, also called RNN-T. It pairs the encoder with a prediction network, essentially a language model running on previously emitted tokens. A joint network fuses acoustic and linguistic features. This auto-regressive design gives the transducer a built-in language prior, making it significantly more accurate on rare words and proper nouns. The trade-off is slower sequential decoding. The first efficiency variant is fast conformer. It replaces the standard two-dimensional convolution subsampling with aggressive depth-wise separable convolutions at an 8-time stride. Acoustic frames jump from 40 milliseconds to 80 milliseconds. Because attention cost is quadratic, halving the sequence length cuts attention cost by 4. The result is 2.8 times faster inference, with the ability to handle over 11 hours of continuous audio and scale to 1 billion parameters. The efficient conformer takes a different approach. It progressively downsamples the sequence between encoder stages. Later stages operate on increasingly shorter sequences, where the quadratic cost is most punishing. It also replaces standard multi-head attention with grouped attention, constraining each head to attend only within a local group of frames. This reduces attention cost from O of n squared down to O of n squared divided by the number of groups. The E-branch former rethinks the conformer's sequential assumption. Instead of processing global and local context in series, it uses two parallel branches. One branch runs self-attention to capture global dependencies. The other runs a convolutional gating MLP for local patterns. Their outputs are merged by learned weights. This parallel design is more stable in early training and matches or beats the conformer across many benchmarks. Let us recap. The conformer was designed because transformers miss local acoustic detail and CNNs miss global context. The input is an 80-dimensional Log-Mel spectrogram. A subsampling front end compresses the sequence by 4. The conformer block is a macaron sandwich. Half feed forward, self-attention, convolution, half feed forward. Inside the convolution module, a GILU gate controls information flow, followed by depth-wise convolution, batch norm, and swish. Decoding is either fast with CTC, or accurate with the transducer. Fast conformer pushes efficiency further with 8 times subsampling. Here is the full picture. Raw speech becomes a spectrogram. The conformer processes it through stacked blocks, each combining attention and convolution. The decoder outputs text. This is the architecture that powers real-time transcription, voice assistants, and multilingual speech systems today. You now understand the conformer from first principles. The problem it solves, its macaron block structure, the convolution module internals, 2 decoding strategies, and how fast conformer and E-branch former push efficiency further. If this was helpful, please like and subscribe. See you in the next one.